And what is up, people? Welcome to this video of boundary layer equations. So yeah, just want to start off by saying hi, welcome. So if you're probably clicking on this video, you'll know that boundary layer equations are pretty fundamental and important part of fluid mechanics. Very important to understand because not everything is a nice pipe geometry. Okay, so let's start off with some blackboard. Okay, we use GIMP. Right, so I don't need this Laplace transform. Yes, so in fluid mechanics, what we are very concerned about, at least from engineering and heat transfer perspective, is something called pressure drop. The pressure drop. Alright, so normally when you have a steady flow of fluid through a pipe, you have the Reynolds number. Okay, you have the Reynolds number, which kind of helps you to determine some kind of friction factor for which you can develop a loss coefficient, or you can get some sort of there will be a correlation for that, for this friction factor, probably using Moody's chart or something like that. So this is what's going to help you calculate pressure drop. Okay, however, not every kind of flow is going to be in this nice pipe geometry kind of a thing. So you probably have, if let's say you were having a tank, having some sort of a tank. Alright, you have a tank, and the tank is like letting fluid like flow into this pipe. Okay, you have something known as an entrance region. Okay, entrance region. So the entrance region, which is over here, I'll just label it ENT. So the entrance region will not have this so-called parabolic flow profile. Alright, it will not have this parabolic flow profile. Okay, this is of course for laminar flow. This strictly speaking for laminar flow. So laminar flow will often have this parabolic shaped flow profile, but at the entrance region you will not have this sort of flow profile. However, at the entrance region you would also have some sort of pressure drop, but it's not going to be well accounted for using the traditional Moody's chart. Okay, so how are we going to sort of deal with that? And then of course the other reason you want to study boundary layers, okay, at least is to give you an understanding, okay, especially for external bodies. So for example, a turbine blade or an aerofoil, if you have some fluid flowing across with some free stream velocity, okay, you have a fluid flowing across with some free stream velocity, it's going to exert a force on this aerofoil or wing. Okay, and what then is going to be the force? The drag force. You can call this FD. What's going to be the drag force that is going to be exerted on this wing? So instead of talking about such complicated shapes first, we like to talk about a flow across a flat plate, okay, where there's some free stream velocity here, and this is a uniform velocity profile, and it meets a flat plate, and somehow when the fluid hits the flat plate, you'll have a no slip boundary condition over here, u equals to 0, and then sorts of develop this little boundary layer. So this is the boundary layer we are interested in. Okay, and of course we start off with a very simple flow profile, which is of course laminar, and we don't want to do 3D stuff first, so we just start off with 2D. If not, it's going to be very complicated. Okay, so these are the basics behind why we want to study laminar boundary layer flow. It gives us a starting point into getting some sort of theory behind how to understand entrance regions and how to quantify the drag the drag force across a wing. Okay, so these are the motivations. Okay, so this video is just to help to establish some preliminary things. I'm not going to go into actual boundary layer equations proper. All right, so but we'll start from the general notation of Navier-Stokes equations, and then we'll work our way down to 2D Navier-Stokes equation, for which we can start dealing with boundary layer equations. Okay, so these are some excuse me, these are some equations I just pulled off Wikipedia. All right, and I'm using LaTeX now, LaTeX to write these equations down. So if you're not sure how to use LaTeX, you can actually observe a little bit in this video, I guess. Of course, it won't be like Microsoft Word presentations where you have like the whole thing in you won't have the whole screen showing the equations. Instead, you'll have some LaTeX code here and some PDF file here for which you can like generate, and you see these equations. So that's what it's going to be like for the next few videos. Of course, LaTeX is good and good to use. It's free, and it produces very nice looking documents, as you can see here. Okay, so I assume you have some basic LaTeX knowledge if you want to look at the syntax, but otherwise, let's just start. Alright, these are equations I pulled off Wikipedia as usual. The first actually deals with the compressible Navier-Stokes equations. Here you have the accumulation term. So within a control volume, you have an accumulation term. How does the mass within a unit volume actually change with respect to time? The second one, this term here is the advection term. All right, how much fluid is flowing in and out of the system? Okay, for this equation in particular, it's a momentum balance. So how much is the momentum changing with respect to time, and how much momentum is coming in and out of the system? Okay, so there'll be fluid carrying momentum into the system and fluid carrying momentum out of the system. And always remember, momentum is a vector, so you'll need to have the x, y, and z components, or the r, theta, z components, or the polar coordinate equivalent of components. Okay, so this is the time change of momentum. This is the advection term, how much how much momentum is coming in and out of the system, because fluid is carrying it in and out of the system. Okay, this is contributed to by the pressure gradient. Okay, this is the pressure gradient bit. Okay, pressure gradient. This next thing here is the Newtonian, what do you call that? This is a stress related, how do you say? This is just a shear stress because of the viscosity of a fluid. Okay, so fluids will have a certain stickiness to it, so to speak. Okay, the fluid isn't exactly frictionless. Okay, and a fluid can exert force on an element of fluid can exert force on an adjacent element of fluid. So for example, again, like this boundary layer here, so when the fluid actually flows across this plate, at the edges of it, the velocity will be 0. Okay, the velocity will be 0, and in fact there will be a shear stress, actually a force. Okay, we just like to call it shear stress because it's a force per unit area, so we'll just denote shear stress as tau. It is acting in the opposite direction of the fluid. Okay, and because let's say the fluid here slows down, it will cause the adjacent fluid elements here to also slow down. I kind of explained this in my earlier videos, so I'm not going to go through that again. So anyway, these are viscous terms, or you can call it the friction loss terms. So that's what this term is about. And of course, for compressible fluids, you can actually lose momentum. Okay, you can actually lose momentum. Okay, so anyway, this term here, It deals with the viscous forces as well. However, you can see this divergence of the vector u here, which means that this divergence of u, it's basically how much, in a more intuitive sense, it's how much net fluid is being put in or put out of the control volume. How much net flow is there into or out of the control volume? It's very similar to this. Del by del T of rho u is how much mass is going in or out of the so-called unit volume, so to speak. And this divergence of u is so similar in concept. How much how much fluid is flowing in and out of the volume, the net flow of it. And somehow this actually contributes to velocity, to viscosity as well, but it's only for like compressible fluids. For compressible fluids, of course, this term is actually drops to 0. Okay, and for our case, we just deal with incompressible fluids for the most part. So for this, we can just neglect it. Over here we will have this gravity term, which of course gravity contributes to static pressure and therefore momentum changes as well. Okay, so yes, you can have gravity actually driving a flow. That's pretty straightforward. Okay. Just before we continue, I want to get us through some nomenclature. This cross over here, O times sometimes this times with an O over it. Okay, that's called a tensor product, also known as an outer product. Okay, so in matrix form, the vector u, when you have a tensor product with a vector v, it will be u, the vector u times the vector v transpose. So you can think of u and v being two different velocity vectors. Okay, let me change some of these notations. Apparently these are actually the same. Okay, so I'm going to change a little bit here. Okay, u, and u. Right, so I'm going to change this part. So I changed the LaTeX code. This is how you actually put a matrix in small little matrix in LaTeX. Alright, so now, yes, this u is u1, u2, and u3. V is v1, v2, and v3. These are vectors. So, yeah, before I continue, I want to just try and compute this so that you will have a hang of what this inner product is about. And just for your information, if you want to start equations in LaTeX, you use the $ symbol. Or the other way is you can do begin equation. Okay, begin equation. I'm just going to use the $ for simplicity. So for $signs, so these will become like your parentheses. And to start, let's try putting this matrix down. So I'll use a begin P matrix. Okay, and to use the P matrix, you'll have to use this AMS math package. That's AMS math. Use package AMS math for LaTeX. Yeah. All right. So let's start. We'll type a u vector. Okay. Vector u. So you want to denote a vector with this arrow across it. You just put backslash vector. Then use this curly braces and you put u inside. That will give you this vector u. For this P matrix, we put the elements in u1. Okay. If you want to like skip a line, I mean go to the next. You wanna go to the next row. So you will type this double backslash u2. So underscore is for subscript and u3. So underscore is for subscript and double backslash is just to put these vectors in. Then I'm going to use the quick build option. And Okay, you will have this. Okay, vector U and U1, U2, U3. Now let's try to put this O times thing here. Okay, this notation, it's backslash O times. Backslash O times, and you select quick build. Okay, I'm deleting the U vector in front, and of course let's put in another matrix. So I'm going to begin P matrix. Okay, V1 double backslash V2 double backslash V3, and I'm going to build. Okay, I forgot. I think I deleted the parentheses by accident. So let's go through how to do this tensor product. Okay, so this preliminaries. If you want to, you can just skip this part. Okay, so let's do the transpose. We transpose the outer side. So the nice thing about LaTeX is you can just copy and paste. Yeah, copy and paste. So I'm going to put P matrix for the second matrix when I'm transposing. I'm going to begin P matrix. Okay, so I want V1, V2, and V3 transpose. So instead of using the double backslash, I'll use double N to denote that they are in the same column or same row, but different column. So if I say V1, if I want to put V1, V2, and V3 in one row, I'll put V1 here, and I'll put double N. I'll put V2, double N, V3. Okay. So those are all in P matrix. Okay, so yes, so this is roughly how the P matrix will look like. This is a little bit white for my liking, so but this is how it would basically go. Okay, I mean the notation is still correct. It just looks a bit ugly, in my opinion. But anyway. So let's see how we can multiply this matrix. So the first row and the first column. Okay, so this will be a 3x3 matrix. When we multiply this out, you can use MATLAB or anything you like. But I will just go through the matrix multiplication slowly. Okay, so begin P matrix. All right. So the top leftmost what do you call that? Top leftmost element will be the first row and the first column. So row 1, column 1 is the first row of the first matrix and column 1 of the second matrix. So that's how you multiply. So U1, V1, okay, and I'm just going to go very quickly. First row, second column, U1, V2, U1, V2, and the first row, third column, U1, V3, U1, V3, and second row, first column, second row, first column, second row of the first matrix, first column of the second matrix. Okay, U2, V1, I'm just going to speed this up, U2, V2, and U3, V3. Okay, let's show you how it looks like so far. I'm going to compile. These are the first two rows of the new tensor that I'm making. Alright, so U1, V1, U1, V2, U1, V3, U2, V1, U2, V2, U3, U2, V3, sorry, U2, V3. Okay. And for the last row, it will be U3, V1, U3, V2, and U3, V3. So I'll have to write that down. U3, V1, U3, V2, U3, V3. Alright. So that's how you do a tensor product. This is also known as an outer product. I'm not going to elaborate too much why, but I'm just going to show you roughly how this is done. And then the other products you will come across in Navier-Stokes equation is this dot over here. It's not always the dot product because dot products are only defined between two vectors. So between two vectors, 1, 2, 3 and 1, 2, 3, you have this u vector and v vector. You can of course take a dot product between them, no problem. But when you have this dot product between a vector and a tensor, it's not really a dot product anymore. It's more of something like the inner product. And how is the inner product defined? There's a proper notation, but I'm not using it here. I'm using something to help like remember how to order your things. Okay, so an inner product between a vector and a tensor, because that's what you will usually come across. Okay, you can calculate the things by just transposing the first vector, and then you leave the tensor as it is. Okay, but this happens to work for a dot product between two vectors as well. So the way you can check whether where to put this tensor, where to put this transpose. One is of course well by the name. Outer product, you can put the transpose at the outer side. Inner product, you can put the transpose at the inner side. Okay, that's one way of remembering. Okay, second way is if this transpose works, if these two are vectors and you use this transpose notation, it should work out to be exactly your dot product as well. Okay, meaning to say if u and v here are vectors, okay, this notation here should be this should be a scalar right over here. There should be a so-called matrix with only one row and one column. So let's show you what this looks like. Again, I'm going to just copy and paste this P matrix notation here, and instead of using the O times, I can use bullet. Okay, bullet is this big dot here. Alright, so what I'm doing is this oh shucks, I do not want these two. Alright, okay, so yeah, basically I just shown you how to do the bullet thing over here. So the it's not going to be the second matrix I transpose anymore, it's the first matrix. So let's put an equal sign. Okay, begin P matrix. Okay, that's not P matrix, begin P matrix. Alright, we're going to transpose this part, so U1, U2 and U3. So U1 and U2 and U3, and then you'll just begin the other P matrix, V1, V2 and V3. So only the first matrix is being transposed. Okay, alright, let me try again. I have some LaTeX compilation errors. Ooh, wonder what's going on here. Oh, I think I forgot my backslash. Alright, there you go. Should work now. Okay. So so when we try to multiply these two vectors out, u1 v1 plus u2 v2 plus u3 v3, it is exactly the dot product. So u1 v1 plus u2 v2 plus u3 v3. Alright, so that's these are basically inner and outer products. Let me put an equal sign there just to make it better. Okay, so these are just ways you can check whether the notation is right. Okay, what what the inner product is like, or dot product. Okay, more generally it's called inner product. What the outer or tensor product is like, because these notations will be used. And once you're more or less familiar with inner product and outer product, you should be able to look at this Navier-Stokes equation without too much fear. Okay. Now, so normally, again, we don't use incompressible flow. No, we don't use compressible flow Navier-Stokes equation. We assume incompressible flow. So assume incompressible flow. And what does it mean? Density is constant. Okay, density is constant. And what else? Okay. If you were to take a look at the continuity equation, I'll just tell you off the top of my head. This divergence of u is 0. Okay, this divergence of u is 0. So that's actually the continuity equation. And I'm not going to prove it here. Okay, so this is a continuity equation. Yeah, I'm not going to prove it here, but if you want to prove it, you have to take a look at some other video. Okay, I'm just laying down the groundworks. Okay, so we assume incompressible flow when we go from here, this incompressible equation, to this compressible flow equation. I'm not going to go through all the steps there because it's pretty tedious and and time consuming, so I'll not do it in this video. But basically, the assumptions to get from here to here and the mathematical methods, how you would go about it after you do all your expanding and everything, is to assume this density is constant and the divergence of u is 0. So this term here will drop out. What you do is to factorize out the density, because density is now constant. So you factorize out density here, factorize out density here, and then you divide the equation throughout on the left and right hand side by density. Okay, you divide the equation throughout by density. Okay, and of course when you multiply this equation out with your tensor product and the inner product, what you'll find is that one significant portion of terms there will result in 0, because again, divergence of u is 0. Okay, divergence of u is 0. So that's why over here you won't have the tensor product anymore, because when you multiply this part out, the tensor product over here, and you take the inner product of this gradient term and this tensor over here, you'll find that almost half the terms drop out. Okay, not quite half the terms, but a fair number of terms. And then you are just left with this expression over here. This over here is actually kinematic viscosity. Okay, again, I pulled it out from the Wikipedia. Okay, this equation form here, you can shift it to the right if you want. It's basically the same thing. Okay, so this term here is just a viscosity term. This term is a pressure term. This term is a gravity term. Pretty much all the terms there remain the same. This term here actually correlates to this one. Okay, so that's these are the groundwork we want to lay before we start, and then we can reduce this equation down to 2D. Then we can start with our boundary layer equation. So thanks for watching. I'll see you guys again. Bye bye.